let's talk about steel. I mean, it's everyone, right? It's the literal backbone of our world, in everything from massive skyscrapers to the humble paperclip on your desk. But what if I told you that inside this totally ordinary material, there's a hidden world of secret recipes and incredible transformations? It all starts with one simple question.
Right? Think about it. How can the exact same basic ingredients, we're talking iron and just a little bit of carbon, create something as hard and deadly as a sword and also something as soft and bendy as a paperclip? The answer isn't in what it's made of, but how you cook it.
And this is the recipe book. Now, I know what you're thinking. It looks ridiculously complicated. Maybe something you'd see in a nightmare about a physics exam. But trust me, we're going to break it down. Think of it less like a scary chart and more like a treasure map for making amazing metals. So, to figure out how to read this map, we're not going to start with a bunch of heavy chemistry. Nope, we're going to start with a surprisingly simple analogy, something you've definitely got in your house right now. Yep, you heard that right. Cloth. Just like a shirt is made of threads woven together, a piece of metal is basically a woven structure of atoms. And how those atoms are woven together, well, that changes everything. So just picture this, okay? A plain red cloth, that's like a pure metal. That's all one thing, like pure iron. Simple. Now, a purple cloth, that's an alloy. You've mixed different atoms together so perfectly, so uniformly, that you can't see the individual parts anymore. And then you've got this, a red cloth with blue dots. This is a mixture. You can clearly see the main red fabric, but you've also got these distinct little blue bits stuck inside it. And that right there is the key to understanding steel. Okay, let's bring back our treasure map. See all those different sections with the weird Greek letters? Each one of those is just a different kind of cloth. By controlling the temperature, that's the up and down axis, and how much carbon you add, that's the side-to-side axis, you get to choose exactly which fabric, which internal atomic structure your steel is going to have. All right, so let's meet the main characters in our little recipe book, the fundamental building blocks, or what metallurgists call microstructures, that actually make up the steel. First up is ferrite. Think of ferrite as the soft, flexible foundation of our steel. Its atoms are arranged in a pretty roomy, open structure, and that's what makes it so ductile. You know, you can bend it and shape it without it snapping. It's kind of the gentle giant of the steel world. Next, we've got austenite. Now, this is steel's super hot mode. When you crank up the heat, the atoms all rearrange themselves into this much more tightly packed structure. The thing is, it can't normally stay this way at room temperature, but it's the magical starting point for all the crazy transformations that are about to happen. And here's the complete opposite of our soft ferrite, cementite. The name kind of gives it away, right? The stuff is a specific chemical compound of iron and carbon, and it is incredibly hard, like cement. But it's also super brittle. You would not want a sword made of pure cementite. It would literally shatter the first time you hit something. So you see the contrast here, right? You've got the soft, bendy ferrite and the hard, brittle cementite. The absolute genius of making steel is figuring out how to combine these two to get the best of both worlds. And this is the brilliant solution, perlite. It's not one single thing, it's a beautiful composite. Imagine a microscopic lasagna with these super thin, alternating layers of soft ferrite and hard cementite. This structure is amazing because it stops cracks in their tracks, making the steel both strong and tough. So we have our ingredients, now for the really exciting part, the cooking. This is where we use heat to perform a kind of alchemy, radically changing the steel's properties. This process, called heat treatment, is actually pretty elegant. First, you heat the steel way up until it turns completely into that high-temperature austenite we talked about. You let it hang out there for a bit just to make sure all the atoms get with the program, and then comes the most critical step of all, cooling it down. Because how you cool it changes absolutely everything. Okay, check this out. If you cool it down really slowly, that's called annealing. The atoms have plenty of time to get organized and form that nice, layered perlite. The result? A softer, more workable steel. But if you cool it insanely fast, like by plunging the red-hot metal into water or oil, which is called quenching, the atoms have no time to move. They're frozen in place, trapped in a super stressed-out, chaotic arrangement. And this trapped, chaotic structure is called martensite. Here's what's so cool about it. You will not find martensite on our original recipe book diagram.
That map only shows what happens when you cool things down slowly, when you let nature take its course. Martensite is what happens when you cheat nature. It's a structure born out of pure chaos and speed, and it is unbelievably hard. This is the secret to making a sword's edge. So far, we've been talking about creating these perfect, ideal structures. But here's a massive plot twist. In the world of material science, perfection is actually a weakness. Real strength, it comes from the flaws.
I mean, this quote just says it all. We're taught to think that pure is always better, but in metallurgy, that's often a recipe for weakness. Just like adding some impure zinc to copper makes brass way stronger, it's the tiny imperfections in steel that give it its true power. These imperfections come in a few different flavors. You've got point defects, which are like tiny typos in the atomic grid. An atom is missing, or there's a different kind of atom where it shouldn't be. Then you have the big ones, dislocations. These are entire extra rows of atoms that are just jammed into the crystal. When metal bends, it's these dislocations that are actually sliding around. And that leads to this amazing process called strain hardening. You've felt this. Ever bend a paperclip back and forth and you notice it gets way harder to bend right at the crease? That's strain hardening. By bending it, you're creating more and more of these dislocations. Eventually, they get so tangled up they can't move past each other. It's like a microscopic traffic jam that makes the material a lot harder. So, we've learned how to build a better metal. We know how to make it strong, how to make it tough, using these incredible recipes and even embracing its flaws. But all of our hard work is under constant attack from steel's greatest and most ancient enemy, rust. See, corrosion, rust, isn't just some random decay. It's a fundamental force of nature. We pump a massive amount of energy into metal to refine it from its natural ore. Corrosion is simply the metal's way of trying to release all that stored up energy and get back to its original, more stable, lazy state. We're in a constant fight against physics.
And this attack comes from all sides. It's not just one simple thing called rust. Oh no, there's a whole army of different types of corrosion, from the general rust that covers a whole surface to tiny destructive holes called pits, to corrosion that only happens in hidden gaps or when two different metals touch each other. The fight to protect our stuff is unbelievably complex.
Which really leaves us with this one last big thought. We've become masters at designing materials down to the atomic level, creating these alloys with absolutely incredible properties. But every single one of them is in a constant struggle against its own nature, trying to return to the earth. So the real question is, in this epic battle between our own creation and nature's decay, can our ingenuity ever truly achieve a final victory?